Great. So yeah, can everyone hear me okay? Awesome. So thank you all for coming. I'm really excited to be here. Today, I'll be talking about quantum gas metamaterials. These are structures we're proposing that can be created using quantum gases. So before I get into the details of this work, I want to start by acknowledging all of the people that helped to get me here today. So first and foremost, I wanted to thank and acknowledge my family. Without them, I wouldn't be anywhere, and they've loved me and supported me at every step of the way. I also wanted to thank my partner, Laurel, who is here. Yeah, she supported me all throughout grad school and even well before that. So I owe her for a lot and for putting up with me for all these years of grad school. And then, of course, I want to thank Jason, uh, he was my advisor for most of my PhD. He really let me study everything that I wanted to study in physics, and he taught me a lot about how to approach physics as a research field. Of course, I want to thank Yuan Ming for taking over as my advisor when Jason became sick. I really appreciate that, so thank you very much. Okay, so just to give some background, my family and I moved from Pakistan to the US when I was 2 years old. We grew up in Tennessee for the most part. I went to undergrad in Tennessee at Rhodes College. There I studied physics and mathematics. Then when I came to OSU, my master's degree, the first 3 years, I spent studying solid state systems, in particular studying some topological properties of twisted bilayer graphene. And then the last 3 years for my PhD, I've been focused primarily on quantum gases. So here's a list of my publications. And this last publication, well, it's not published yet, but hopefully within the next month or so it will be. That's what this thesis is going to be about. On the side, I've also been doing quite a bit of machine learning work. And so after graduate school, my plan is to go into industry, doing some superposition of machine learning and quantum physics. Okay, so before I get into the bulk of the research, I want to just lay out the order of operations. The very first thing I'm going to do is give some motivation for why physicists study quantum phenomena, and in particular, why we study quantum gases. Hopefully, this will be useful for people in the audience who aren't too familiar with the field. After that, I'm going to introduce the concept of a quantum droplet, which is a particular type of BEC that was very recently discovered. After that, I'm going to show how quantum droplets can be used and stabilized in a variety of different topological structures. Great. So quantum mechanics was discovered around 100 years ago. And from its discovery, we learned that the microscopic world behaves very differently from our everyday reality. Now, the early experiments in quantum mechanics were studying single particle systems or systems with a few particles. However, there's an ongoing push in physics research to study the effects of quantum mechanics at the large scale. Even a single drop of water has 10 to the 22 number of particles. And so the question is, when you have this many particles in a system and they behave in a quantum way, do we get any interesting behavior out of that? I'm going to refer to this large-scale behavior as macroscopic quantum phenomena. And there's a few standout examples of this that are well studied that I just wanted to touch on briefly. So a common theme that you'll notice is that in order to see the effects of quantum mechanics, in many cases, you have to make the system very cold. So going in with that mentality, first I wanted to talk about superconductivity. In a typical wire, just made of metal, when you run electricity through it, this generates heat. But in many cases, if you cool down the metal to a sufficiently low temperature, and then you run electricity through it, it actually behaves like a superconductor, which means that electricity passes through it without generating any heat. So this is basically what allows MRIs in hospitals to function. Superconductivity also turns out to be a fundamental part of what makes modern quantum computers work. Another type of macroscopic quantum phenomena is superfluidity. So if you take helium and you make it very cold, it becomes a liquid. And if you make it even colder than that, it becomes a superfluid, which is a liquid that doesn't feel any friction. And so if you put a superfluid helium in a bowl shaped like this, and you get it spinning, then it will keep spinning until the end of the universe, as long as you can pay the cooling bill. Okay, so there's some very dramatic properties that we can see at the macroscopic scale because of quantum physics. The particular type of macroscopic quantum phenomena that my research has been focused on is called Bose-Einstein condensation. In particular, I'm studying this in ultra-cold dilute gases. Now, I'm going to break down what all of these words mean, but first I wanted to give us a sense of scale. So how dilute are these gases? Well, they're around 100,000 times thinner than air. Okay, and then how cold are they? So they're held at about 20 nanokelvin, which is 15 billion times colder than room temperature. So these systems really are working at the extreme ends of nature. Now, typically, when you're thinking of a gas, you might be imagining a bunch of particles bouncing around, colliding off of each other. And in many cases, this is a reasonable picture. However, it turns out that when you make the system very cold and very dilute, this is no longer a useful picture to keep in mind. So previously, you might have thought of a particle as something that moves around with this definite position at all times. Well, when things get cold and quantum mechanics sets in, particles no longer behave like this. Instead, particles tend to spread out and act like waves. So what do I mean by that? Well, instead of having this definite position, the position of the particle is essentially spread out. And the amount that it becomes spread out is called the de Broglie wavelength. This is basically the width of the wave. Now, I've given the equation of the de Broglie wavelength right here, and we can see that it's inversely proportional to temperature. So the colder you make the system, the more the particle spreads out and acts like a longer and longer wave. Now, when particles behave like waves, they no longer see each other as particles to just bounce off of. They see each other as waves. And waves can constructively and destructively interfere with each other. So let's go back to imagining a bunch of particles bouncing around in a box. Okay, so that'll look like figure A. Now, as we make the system colder, these particles become more like these waves that I was just describing. As we make the system colder and colder, the width of these waves continues to spread out. Eventually, many of these waves are getting to the same size as the box itself. Now, in the most extreme limit, when things are very, very cold, all of the waves are the same size as the box, and they all become perfectly aligned. Now, since you have so many waves, all perfectly aligned, they're all adding to each other constructively. And so the originally microscopic effects of quantum mechanics become amplified to the macroscopic scale. Okay, so this was a simplified picture of what Bose-Einstein condensation is. It's the condensation of all of these waves into basically the same, all of these particles into basically the same wave. So a Bose-Einstein condensate was first created in an ultra-cold gas in 1995, and this led to a Nobel Prize for Cornell, Ketterle, and Wyman. So what is the big deal about BECs? Why are people so interested in them? Well, it turns out that this condensation is the fundamental mechanism behind superconductivity and superfluidity, which I mentioned earlier. In addition, these ultra-cold gases are very easy to tune experimentally. So experimentalists are able to change the interactions between the atoms, apply a variety of different external potentials to change the shape of the gas, and even consider mixtures of different condensates. So this lets them pursue and explore a wide variety of different macroscopic quantum effects. In addition, these systems are very clean. So there's a very direct correspondence between what's happening at the microscopic level and what's happening in the experiment. And so it's very easy to understand and predict what we expect to happen in the experiment. Now, the simplest description of a BEC that's interacting is given by the so-called Gross-Pitevsky equation. In this equation, psi here refers to the wave function of the condensate, and then psi squared is the density of the condensate. And so this overall equation tells you the energy of the system. The first term corresponds to the energy cost of variations in the density. The second term corresponds to the energy from the atoms in the condensate interacting with each other. And then this third term corresponds to the energy of some external potential. For example, experimentalists often apply external potentials to confine the gas. Now, let's just look at this interaction term for a moment. And we see that the strength of these interactions is tuned by this parameter g. So if g is positive, this is called repulsive interactions, because in order to minimize the energy with a positive g, we'll want to make this n, the density, very small. This corresponds to the gas spreading out. Now, if all we had was the interacting gas without any external potential, we can see just from this term that the gas would spread out, wanting to minimize its density. It's this external potential that confines the gas and lets us hold it in place. So that's what I'm showing in this figure on the right-hand side. This blue curve represents some kind of harmonic potential confining a cloud of atoms. As soon as we turn off this potential, setting V to 0, then the gas is able to spread out due to its interactions. Okay, so if we consider a uniform gas, we can just ignore that gradient term that we were just talking about. And then the energy density of the system just has this interaction term. Now, for those who are familiar with cold atom research, you know that the Gross-Pitevsky equation is a lowest order approximation. Okay, in this equation, we're assuming that all of the atoms in the system are in the condensed state. We know, however, that this isn't actually what's happening at the physical level. Even though there is a macroscopic occupation of the condensed state, because of the interactions, there's actually fluctuations of particles out of the condensed state. These quantum fluctuations are beautifully captured by what's called Bogoliubov theory. So if we go through the derivation of the Bogoliubov Hamiltonian, we actually find that the energy of the condensate is modified by the fact that there's particles that fluctuate out of the condensate. This modification leads to a higher order term called the Li-Huang-Yang correction. And so that's what I've put here. This was discovered in 1957. Now, in most descriptions of BECs, this term actually isn't included at all. That's because the magnitude of this term, it contributes about 1 to 2% of the total energy. So its effect is very, very small. In fact, it was very difficult to even experimentally measure its effect. Okay, so I just wanted to mention that because it will be useful for us going forward. This was our understanding of BECs until very recently. In 2015, there was this beautiful theoretical proposal by Dmitry Petrov. He showed that it's actually possible to make a BEC where even when you turn off this external confining potential, the cloud of atoms doesn't float away. Instead, they remain self-bound. This has become known as self-bound quantum droplets. Okay, and so these were first experimentally realized soon after the theoretical proposal, and since then, they've become a very active area of research in the cold atom community. On the right side, I've just listed a few of the recent experiments that have been done, but there are many experimental labs who are pursuing research in this direction. It's led to the realization of many never-before-seen quantum effects, including the creation of new types of quantum vortices, and there's evidence that they've been able to use these quantum droplets to create the so-called supersolid phase of matter, which had been sought after for over 60 years. Now, in this figure below, this is data from the very first experiment done on quantum droplets. And they're comparing a typical BEC, which they've labeled a gas, to a quantum droplet. Before time t is equal to 0, they start both of these gases confined. Then at time t is equal to 0, they turn off this confinement and let the gas expand to see its behavior. Now we see that in the gas, the typical BEC, it expands out the way you would expect, just the interactions are causing this gas to float away. However, we see with a quantum droplet that it retains its self-bound shape even without external confinement. Okay, so we're seeing this dramatic change in behavior. So what is Petrov's secret? Like, how is this happening? Well, it turns out that Petrov is considering mixtures of two different BECs. And in particular, he's tuning the interactions of the system such that this mean field energy cancels out. And so the Li-Huang-Yang correction in this system now becomes very important. So let's see how this happens in a little bit more detail. Earlier, I showed the energy density of a single component BEC that's uniform. we can generalize this easily to a mixture of two different BECs. Now, these first two terms correspond to the self-interactions of each BEC, basically each gas repelling or attracting itself. And then this third term corresponds to the interactions between the two different BECs. We can rewrite this energy in a form that's slightly more useful to us. So here I've introduced this parameter delta G, which is a combination of the interspecies and intraspecies interactions, as shown here. Now let's consider a particular limit. Let's say that the interaction of each BC with itself is positive or repulsive. And then we tune the interactions between the two different BCs to be attractive or negative, such that this parameter delta G becomes very small. Okay, so keeping this in mind, let's look at our energy density again. If this delta G is very small, then this first term is the most important piece of the energy. In order to minimize the energy of the system, this first term will have to go to 0. And in order to make this first term 0, you can see that the densities of the two different BECs have to be locked to each other. And they have to satisfy the following ratio, that n1 over n2 is equal to the square root. Okay, so in order to minimize the energy of the system, in this limit, we're considering the densities of the two BECs locked together. So if there's more of one BEC in one area, then there's more of that other BEC in that area as well. Since the two densities are locked together, we can effectively treat this system as a single component BEC, where instead of talking about the densities of the two individual gases, we just have this density n, which refers to the density of the mixture. And in this limit, the energy now looks like delta G n squared. This looks exactly like the energy of a single component BEC. However, instead of our interaction parameter G, in this case, we have delta G. Now, we can ask ourselves, what does the Li-Huang-Yang correction look like for a mixture of two gases? So this is actually derived by Larson back in 1963. He didn't realize that this effect could be made useful in order to make quantum droplets, but Petrov simply used this result to prove his point. So let's take a look at what it looks like in this case. We still have our delta G n squared corresponding to the effective single component mean field energy of our mixture of two gases. And then we have the second term, which is the Li-Huang-Yang correction for this mixture. And we see that this is controlled by the parameter G11 and then this alpha LHY. This alpha LHY is a function of G11 and G22. So what does this tell us? Well, even in this two-component case, the Li-Huang-Yang correction is very small, okay? But in this case, it's controlled by G11 and G22, whereas we can independently tune the mean field interaction delta G because it's a different parameter. And so we can make delta G very small so that the Li-Huang-Yang correction becomes very important to the system. Not only that, but we can consider delta G to be negative. Now, let's ignore the Li-Huang-Yang correction for a second. If delta G is negative, then the energy of the system is minimized by the density going to infinity. This is known as the mean field collapse of the BEC. However, in this case, even though a negative delta G at the mean field level wants the density to diverge, if we include the Li-Huang-Yang correction, since it scales faster with density, since it's n to the 5 halves, this actually prevents the density of the system from diverging. Let's take a look at this in a pictorial form. So here I've plotted the energy versus the density. This blue dashed curve corresponds to the mean field energy with a negative delta G. So it just looks like a parabola going downwards. Then this red dashed curve corresponds to the Li-Huang-Yang energy, which is positive, and it scales faster than the mean field term. So when we add these two terms together, we find that the energy of the system isn't minimized by the density going to 0 or the density going to infinity. Instead, the energy of the system is minimized by the density taking this finite value. So the system wants to maintain this finite value, and this causes the gas to become self-bound because it doesn't want to spread out forever anymore. Okay, so if we have the density of the mixture, which on this slide I'm referring to as phi squared, we can easily convert back to the densities of the two different species of BECs by multiplying by this constant gamma 1 or gamma 2. These constants are just functions of the interaction parameters. Now, here I've written out the full energy for our system, including the Li-Huang-Yang correction. So this first term is just the full Gross-Patevsky equation, where I've included any external potentials we might consider, as well as a chemical potential term. And then this is the Li-Huang-Yang correction. Now I've written this in a unitless form, absorbing all of the units into our position coordinate r tilde. Something important I wanted to point out here is that in this form, the energy of the system is minimized by this equilibrium density of 1. This is going to turn out to be important because stretching the droplet away from this density turns out to have an energy cost, and this leads to something like a surface tension. So these are simulations that I did comparing a typical repulsive BEC to a quantum droplet. And I just wanted to show them to you so that you have a more intuitive idea of what the difference here is. So the red corresponds to a confining potential, and then the blue is the density of the droplet. We see that as we move the walls away from a typical BEC, the density of the BEC continuously decreases, and the gas expands out to fill in the walls of the container. On the other hand, as we stretch the walls away from a quantum droplet, the density decreases until it reaches its equilibrium ideal density. After that, it maintains its self-bound shape. So, where does my work come in? Well, we're suggesting using these quantum droplets to create a variety of different non-trivial structures. So the first project that I'm going to talk about is going to consider using external potentials to cause this quantum droplet to stabilize with different curvatures and different non-trivial topologies. This is useful because it turns out that, well, it's been well established that many quantum systems behave differently depending on the topology of the system that they're on. So in many cases, it matters a lot whether the system is in the shape of a sphere or it's in the shape of a donut. But it's notoriously difficult to experimentally create systems in the shape of a donut. So that's where this part of the project comes in. We're going to suggest ways of making a quantum system that can stabilize in these different shapes. In addition, we're proposing using quantum droplets as a method of combining other quantum gases into larger scale structures, which we call quantum gas metamaterials. This is an analogy with metamaterials in solid-state physics, which are artificial structures made by combining different solids to have properties that surpass what's typically possible in nature. So we're hoping that these quantum gas metamaterials can be used to create exotic quantum systems that show properties that haven't been possible to see before. So here's just some examples. We're going to start with a spherical quantum droplet. And then I'm going to show how we can stabilize it in this donut shape or in a spherical or toroidal shell. And then I'll also consider creating macroscopic lattices using the quantum droplet along with a third BEC. Okay, so the first thing we're going to consider is stretching the quantum droplet into a film. So this is important for a few reasons. First, if we want to use these quantum droplets in order to create these larger scale structures, then having an understanding of the elasticity of the quantum droplet is of fundamental importance. Secondly, it turns out that if we stretch the droplet into a film and puncture it using some kind of laser, then we can actually stabilize holes in it. This means that we can create a quantum system on a closed manifold where we can easily change its genus. So experimentally, one method of creating such a film would be starting with our spherical quantum droplet and then applying two attractive lasers on either ends of the droplet, which basically grab onto it. Then we can pull these lasers apart, stretching the quantum droplet into a film in between. So this is like a naive experimental picture, but the question is, what actually happens when we stretch the droplet? Is it actually stable? So in my numerical simulations, I'm considering a 3D droplet that's uniform in all directions that I stretch in one direction. Now, in these plots on the right side, the y-axis corresponds to the density, and the x-axis corresponds to the direction along which we're stretching. So in figure A, we haven't introduced any potential yet. So there's no attractive potential. And so we just have this droplet stabilized at its equilibrium density of 1. Moving on to figure B, we implement these two attractive potentials shown in red. We're modeling them as these thin Gaussians. We see that it grabs onto the edge of the droplet, stretching it out and decreasing the density at the center. Now, in the subsequent figures, I'm simply stretching the droplet out further by moving these two lasers apart. And the question is, what is the fate of the droplet? Can we keep stretching it forever, or is there some critical lower bound on the density? It turns out that there is. We can stretch the droplet until the density at the center reaches 0.64 times the equilibrium density. If we try stretching it any further, then the center of the droplet collapses, and we end up with the system forming these two different droplets centered at the attractive potentials. Okay, so this gives us a better understanding that the droplet can stretch, but there's a limit to how far it can stretch. And the question is, where does this limit come from? To understand that, let's look at the energy density of the droplet in the bulk, so in the center. Here I've plotted the energy density for a variety of different chemical potentials, so we get this family of curves. Now, the important thing to remember is in order for the droplet to be stable at a particular density, that density has to correspond to a minimum in the energy. That's what it means to be stable. So this lowest curve here, corresponding to mu is equal to negative 0.5, corresponds to the equilibrium density. We see that the energy is minimized by the system having this density of 1. Then we can consider other curves by changing the chemical potential mu. And we see that as we make mu decrease, this curve, the minimum in the curve, moves upwards and begins to flatten out. Once we get to this mu of negative 0.64, this minimum has totally flattened out and is now a saddle point. And if we decrease mu any further, we see that there's no longer any finite minimum in the energy. So what does this tell us? Well, we can see clearly that there's no minimum in this energy curve for a density below this value of 0.64. So that's why it's impossible for the system to stabilize with a density below this value. Okay. So we also implemented this stretching idea in 3D. We used a cylindrically symmetric attractive potential in the shape of a thin shell. So in the radial direction, it's still a thin Gaussian, and that Gaussian is centered at this black dashed line. And then in the z direction, it's constant. And then we're simply increasing the radius of the cylinder to stretch the droplet out. In this case, we see similar behavior as before. So we start with this droplet, it becomes stretched out into a film, and then it reaches some critical density in the center. If we try stretching it past this value, then the center collapses, and in this case, the droplet takes the shape of a ring. Sorry, excuse me for one second. Yeah. Yeah. Like, do you mean in this equation I'm ignoring it? So here we're just writing down the energy density in the bulk. So the bulk is like where it's flat, right? So there is no gradient term. So
when you are stretching it,
Mhm.
as I can see that one of the previous the shape is actually changed. Where the external potential is.
Yeah. So like for example, you're right that like in the 1D case in the bulk, it's still flat even when you stretch it, so we can ignore the gradient term. In the 3D case, it's obviously not flat because it's changing in the z direction here. So we do still have to use a gradient term, or like keep the gradient term in the energy. But it turns out that the same analysis applies and it has the same critical lower bound on the density, even with like that gradient term included. Oh yeah. In the numerical simulations, it's the full thing. Yeah. Yeah. Yeah, thanks for the question. So another idea we consider is using external magnetic fields to stabilize the quantum droplet in a variety of different topologies. So how does this work? Well, typically, a BEC is made using alkali atoms, and these atoms couple to external magnetic fields through the Zeeman effect. What basically happens is that the atoms are pulled in the direction of increasing field strength. Okay, so if we have some magnetic field that's changing in space, we can use that to stretch our quantum droplet out and stretch it into these different configurations. Now we'll be considering two types of quadrupolar magnetic fields. We're considering these two because they're readily available in most cold atom labs already, okay? Because these fields are typically used to actually confine gases. In this case, we don't need external confinement, so we're suggesting using these fields that are already there to create new configurations with the quantum droplet. So this type 1 field is constant in the z direction, and then its strength increases as you move radially away from the z-axis. This type 2 field, its strength also increases as you move radially away from the origin, but it increases faster as you move in the z direction. Okay, so let's start by looking at what the Zeeman effect does from a type 1 field on the quantum droplet. So in this case, the Zeeman potential has the following form: negative lambda times r, which is the distance from the z-axis. And so this has the effect of stretching the quantum droplet out in the radial direction, effectively flattening it in the z direction, giving it this sort of pancake type shape. Now, if we're able to puncture the center of the droplet, for example, using some kind of laser, then what we end up with is a ring. And the Zeeman effect will try to continue to stretch this ring in the radial direction. Now, it can't stretch the ring forever. Like I mentioned before, the droplet has this equilibrium density of 1 that it wants to maintain. If the Zeeman effect kept stretching it, then it would be stretched away from this equilibrium density. So in fact, you get a stable ring when the Zeeman energy balances with this surface energy of the droplet not wanting to be stretched too far. Okay, so this gives us a method of creating stable rings in an external magnetic field. It turns out that you can't use a type 2 field to create this sort of stable ring. However, we're not done. There's still plenty more interesting things you can do. Another thing we're suggesting is using the rich internal structure of the atoms in the BEC to generate non-trivial effective potentials that act on the gas. So by rich internal structure, I'm referring to the spin. Remember that our quantum droplet is made by the mixture of two different BECs. Now, let's say that both of these BECs are composed of spin 1 atoms. Now, if we apply an external magnetic field, the spins of all of these atoms from both BECs will align with that external field. Let's consider the case where the external magnetic field is strong enough that it forces all of the atoms to perfectly align with the field. That means that each of those two BECs has the same spin at each point in space. And so our quantum droplet, which is the mixture of both BECs, also has that same spin. Okay, now, this means that our quantum droplet is also effectively a spin 1 condensate, just like the underlying two BECs are. In order to capture the spin 1 structure of our condensate, we have to generalize our wave function. Before, it was just a scalar that told us the density, or the square root of the density, at each point in space. Now we have two pieces. We still have this second piece phi corresponding to the density of the droplet at each point. But now we also add on this term zeta which is a 3-component vector. It tells you the spin at each point in space. Okay. Now, if we are saying that the spins of the droplet are perfectly aligned with our external magnetic field, then if we parameterize our magnetic field in spherical coordinates, like I've done here, then we can explicitly write down what our spin function zeta is. I mean, it's given directly in terms of the magnetic field, and I've written down the relationship here. Now, remember that our quadrupole magnetic fields are varying in space. This means that our spin is also varying in space. And this spatial variation of the spin leads to an additional energy. This comes from that gradient term in the energy we had before. So let's take a look at the gradient term. Now we can expand it using the chain rule. And in addition to this gradient and density term that we had before, we have this new term corresponding to the change in spin. We call this term W bar, and it acts like an effective potential acting on the quantum droplet. So using this method, by applying an external magnetic field and taking into account the spin, we're able to create additional external potentials on the system that might be otherwise difficult to create. So let's take a look at what effect this has. For a type 1 field, this term W bar has the form of 1 over r squared, where r is the distance from the z-axis. And so its effect, shown in this plot where I'm plotting both W bar and V bar, is to be strongly repulsive away from the z-axis. Now, as we get further away radially, then the Zeeman term kicks in, and that continues to stretch it in the radial direction. Now let's take a look at how our quantum droplet stabilizes if its spins are aligned with the magnetic field, and so it feels this effective potential. We get the following shape. The figure is a little bit misleading. It might look like it's a donut. In fact, the density is 0 exactly at the origin, and then it increases as you move radially away. It increases continuously. So it's only 0 directly at the center. We can change the curvature of this shape by tuning the strength of the Zeeman potential. So this gives us the ability to create a structure where we can change the curvature of the shape. Now we can also look at what alignment with a type 2 field does. In this case, I've plotted the effective force from the Zeeman potential and the spin alignment potential on the right side here. We see that close to the z-axis, the behavior is similar to what we saw before. It's strongly repulsive away from the z-axis. And then as you move further out radially, that's where the Zeeman potential kicks in, which preferentially stretches the droplet in the z direction. So in this case, our quantum droplet stabilizes in this full donut type shape where there's a hole with a finite radius at the center. Now, if we start with a small number of particles, then our droplet is confined closely to the center, and you get a typical donut or ring type shape. But if we consider a larger number of particles, then the droplet is able to stretch out further in the radial direction, and that's where this Zeeman force becomes important, and it stretches it out in the z direction. So for a large number of particles, the system stabilizes as more of a hollow cylinder type shape, where it's stretched out in the z direction. Once again, we can change the curvature of this shape by changing the strength of the Zeeman potential. Okay, so far we have been talking about creating these stable structures with non-trivial topologies by applying external potentials to our quantum droplet. We want to also consider something totally different. We want to consider systems made of 3 gases. So we're introducing a third BEC that's repulsive with the quantum droplet. The physics of a 3-component BEC system are much richer than what we were looking at before. In this case, I'm going to show that we can create structures using the quantum droplet confining the other BEC that have non-trivial topologies that don't require any external potentials in order to stabilize. Okay, so since we're considering a third BEC that's strongly repulsive with the quantum droplet, this third BEC basically sees the quantum droplet as a hard wall. This allows us to use the quantum droplet as a bubble or a bag to confine this third BEC. Now, the overall energy of the system is now given as follows. We still have the energy of the quantum droplet, including the Li Huangyang correction. In addition to that, we add on this third BEC. So this is just the typical GP equation for a repulsive BEC. And then we have this last term corresponding to the repulsive interactions between the droplet and our third BEC. The first thing we're going to consider is creating something that looks like a spherical bubble. So how is this going to work? Experimentally, we can imagine starting with both the quantum droplet labeled AB here and the third BEC labeled C, confined by harmonic potentials in the lab. And in particular, we want the potential confining the third BEC to be tighter and centered in the middle of our quantum droplet. Then, as we adiabatically turn off the confining potentials, this third BEC begins expanding because it wants to minimize its internal pressure. Since the quantum droplet sees it as a hard wall, it's going to press against the quantum droplet, stretching it out as well. Now, the story is the same here as what we talked about before. Even though this third BEC wants to stretch out to reduce its internal pressure, the quantum droplet doesn't want to keep stretching forever. It has this limit. And when these two energy scales balance, you get a stable bubble. So that's at least an intuitive idea of how this might work. But the question is this actually stable? Well, our numerical simulations find that this is indeed stable for a wide variety of interaction strengths and numbers of particles. So using this method, without any external confinement for stabilization, we have this three-component gas that is self-bound, and the quantum droplet is making this non-trivial shape. It's making the shape of a spherical shell. Natural questions here are, how does the equilibrium radius of this bubble change depending on the interaction strengths and the numbers of particles? In addition, you might ask, if I keep dumping particles into this thing and the bubble keeps expanding, does it pop eventually? So we answer both questions, and I go into detail about them in the thesis. Here, I just wanted to go over our study of the equilibrium radius. So we propose a theoretical model to predict the equilibrium radius for both a weakly self-interacting BEC and a strongly self-interacting BEC. And the radius predicted by our theoretical model is shown in the dashed red line. Then I simply measure the actual stable radius using numerical simulations. We see that there's this very close correspondence between our theory and what we get numerically. Yeah. So the theory prediction is we approximate the energy of the quantum droplet in the spherical shell shape, plus the energy of a weakly interacting BEC with some radius. And then using that, we just minimize the energy in terms of R, the radius of the bubble, and see what radius of the bubble minimizes the energy.
If I keep on increasing the bar, it would break at some point because you cannot stretch the droplet.
Yeah, exactly. Yeah, actually, so here, both of these lines that I'm showing, like they end at pretty much where the bubble bursts. So yeah, there's this hard limit. Thanks. We can also consider more exotic shapes, for example, creating a toroidal bubble confining a third BEC. So in order to make a shape like this, we would start with the spherical bubble we were just talking about. And then you can consider applying a repulsive laser that only affects that third BEC on the inside. This would puncture that BEC, making it form this toroidal shape inside a spherical quantum droplet. Then we can apply a thinner repulsive laser that acts on the quantum droplet itself. That will puncture its center, making the shape effectively look like a torus of the quantum droplet surrounding the third BEC, like this. So the question is, once again, are these structures stable? And indeed, they are stable. We find these structures to be stable for a variety of different numbers of particles and interaction strengths. And once again, this stability is coming simply from the fact that the surface tension of the quantum droplet is balancing with the internal pressure of the third BEC. And so even after, at this point, we've turned off the lasers and the structure is remaining stable. Okay, the last thing I wanted to talk about here was the possibility of making macroscopic lattices from combinations of the quantum droplet with a third BEC. This would be a simple example of what I was calling a quantum gas metamaterial. I'm going to show you that by changing the number of particles per unit cell, the system actually goes through a structural transition. So how would you make a lattice like this? Well, we can start with our quantum gas bubble. In this case, it would have to be a large one. And then we apply an optical lattice that only affects the third BEC. The effect of this optical lattice would be to break this third BEC into a bunch of small pieces. Now, once it's broken into these pieces, the quantum droplet, since it's not affected by the optical lattice, will rush to fill in the gaps. Okay, then we can adiabatically turn off the optical lattice, letting these pieces of the BEC to expand into these orbs. And these orbs will make a lattice in the shape of the original optical lattice. Now, as I mentioned, by changing the number of particles or the interaction strength per unit cell, we can actually induce this transition from two very different structures. Let's take a closer look at the unit cells to see what's going on here. So for some number of particles, we start with the third BEC making these orbs inside each unit cell, surrounded by this hard wall of the quantum droplet. So in this case, these islands of the third BEC are totally independent from each other. So there's no overall correlation or coherence between these different islands. Now, as we either make this third BEC more repulsive, or we increase the number of particles of the third BEC in each island, these islands start to expand, and eventually they touch each other. So once they can start talking to each other, all of the islands all of a sudden become coherent. And you get this macroscopic structural transition. Another way to think about this new structure is that now you have islands of the quantum droplet separated by hard walls formed by the third BEC. So yeah, I should have clarified this earlier, but in this figure, the peach corresponds to the third BEC and the purple is the quantum droplet. Okay. So we map out this transition using our tuning parameters. So as a function of the number of particles of each type per unit cell and the interaction strength. And we see that there's this sharp transitioning from a lattice of droplet islands to a lattice made of the third BEC islands. Great. Yeah, so those were the main results that I want to share with all of you. I just wanted to go over some future directions here. So we consider two very simple types of magnetic fields that can be used to generate external potentials, but there's an infinite number of possibilities that you could consider. So that's an obvious direction that people can pursue. Another idea is the possibility of using other quantum gases and combining that with the quantum droplet. So in our case, we just consider a very simple BEC, but theoretically and experimentally, they could consider a Fermi gas or anything else that's not well understood and see how it behaves with the quantum droplet. Now, these lattices I was just considering have very interesting excitations because not only can these islands vibrate, but they can have particles tunnel from one island to the other. And so it would be very interesting to study the excitations in these lattices. And then just moving forward, hopefully this has been setting some building blocks up for the creation of larger scale structures. So I would be very interested to see people create these building blocks and then combine them to make more interesting structures going into the future. Okay. Yeah, well, thank you all for your attendance. Yeah.
So going back to when you were showing the lattices and making the lattices, how do you create an optical lattice that would only work on the VLC and not puncture your droplet?
Yeah, so it turns out the way these optical lattices work, well, there's a few different forces at play, but one of the major forces is the dipole force. And so you can change the frequency of the laser, and depending on the frequency, sorry, let me take a step back here. So each atom has this fundamental frequency coming from the energy difference between the lowest and second lowest energy levels. By tuning the frequency of the laser can either be attractive or repulsive if it's below or above the fundamental frequency of that atom. And so if we had an atom for our third BEC that had this fundamental frequency very different from the atoms for the optical lattice, then we can have an optical lattice that only affects this third BEC. Yeah, thanks. Yeah.
So you said there's a transition from different type of time.
Yeah.
Like, is it a not a phase transition, like, is it a difference also?
So I would call it a type 1 phase transition because basically what's happening is these are two different ground states with different energies, and then at this transition they both have the same energy. So yeah, I would call it a first order. Yeah. Sure, yeah. Could you read it off? Yeah, thanks.
I've touched on the creation of quantum shape and system, but could you expand on potential and uses of Spencer planning?
Yeah, thanks, Spencer. Yeah, so well, nowadays, there's a lot of active research. For example, there's systems where if you can make them in the shape of a donut, it turns out that you could use them to make stable quantum computers. These are called, topologically ordered systems. Even in the case of something simple like a BEC, it turns out that BECs can have something called vortices, quantum vortices. And the number of quantum vortices you can put on a BEC depends on the topology of that BEC. This is due to the so-called Poincare-Hopf theorem in mathematics. So yeah, that's one simple example of the effects of quantum mechanics depending on the topology of the system. Maybe more fundamentally, you might be wondering, like, why do we care about creating these shapes? This seems like a very simple thing to do. And I would agree, it is simple, but I think that speaks kind of to our infancy in the field. Imagine we had just discovered fire 100 years ago. We discovered quantum mechanics 100 years ago, and the first BEC was made 30 years ago. Obviously, our understanding is much better than that, but experimentally, it's still very difficult to do things that sound very simple. There's a lot of room to grow. And so hopefully, what we're talking about here serves as some first steps for addressing this issue in the case of quantum gases. Sure. Right. Yeah. If I was a little more familiar with how experimental doping works, I could say more, but my guess is it would be a lot of, so like, I guess you're imagining building this lattice, and then we could have this like shape, impress itself on the structure. Yeah, I'm not too familiar with how they do it experimentally, but my guess is it would be a lot more work that way. Yeah, maybe Jay, you can say something about that. But my understanding was that when they're making these lattices, sorry, like in a solid state setting, the gas that they're combining is like very hot. And so uh, the I don't know how that would work with the BEC that's super cold. Yeah. 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 Yeah, thanks for the question.
There's one more question.
Sure.
From that in that, have you experimentally shown the coupling of the different quantum?
The coupling, like the interaction strength? Yeah, that's something called the Feshbach resonance. So it turns out that this is like a very long story, but in short, by changing the static background field around some critical values, you can change the effective scattering length of the atoms. And so it turns out that each atom has this very precise value. And then if you move some static magnetic field in the background around this value, then you can make the atoms very attractive or very repulsive. This is something that makes alkali atoms so amazing, is that we can tune these interactions so freely. Yeah, there's a very long story there. I could go into it, but yeah, that's just like a very simple picture of it.
Not, I think it's time to add the public.
Yeah, sounds good. Yeah, yeah. Cool. Yeah, thank you all for coming. Appreciate it. Thank you for everyone who came in the Zoom session. Yeah, I appreciate your support.